Chapter 7, Laplace transform. So Laplace transforms convert function from time domain to the x domain. So this formula is the definition of the Laplace transform. Original function is the ft, so in the time domain, t for time. Then L, the ft, so L is for the Laplace transform. So equals capital Fs. So now capital F function is in S domain. So equals integrated from 0 to infinity, positive infinity. Then e power to the minus st times ft dt. So t is the variable. So this Laplace transform again convert function from the time domain to the x domain, to the s domain. If we get a function in s domain, so we can use inverse Laplace transform. Convert the function in s domain back to the time domain. So inverse, so L power to the minus 1, that is for inverse Laplace transform. Fs equals ft. So this is a very simple example. So ut equals 1 when t is greater than or equal to 0. If t is less than 0, so ut is less than 0. Then use the Laplace transform of ut. So equals integrated from 0 to infinity 1 times e power to minus st dt, so equals minus e power to minus st over s, then from 0 to infinity. So we get the result is 1 over s. For derivatives, so f prime t, so this is the first order derivative, equals df by dt, right? If we use Laplace transform on both sides of this formula, so L f prime, so equals integrate from 0 to infinity df by dt times e to the minus st dt, dt over dt, so they cancel out. That's the integrate from 0 to infinity e to minus st df. Then use the partial integration, so we can get f times e to the minus st, again from 0, t from the 0 to infinity, plus s, then integrated from 0 to infinity f e to minus st dt. Then for this integration, so we know it's just the Laplace transform for the original f, right? So this is the s times l f. Then this is just the constant minus f0. Then in general, for n order derivative, so L fn equals s2n times lf minus s2n minus 1 f0 minus s2n minus 2 f prime 0 minus minus onto fn 0. This table shows some of the functions Laplace transforms. Okay, so for example, we talked about this before. So 1, then 1 over s. Sin at, so that's a is constant. So a over s squared plus a squared. Cosine at, so it's s over s squared plus a squared. Eat, 1 over s minus. So this is some useful functions for Laplace transform. Then this is for the integration. So integrate 0 to t fv dv for fs over prime. So here, first order derivative, then order derivative. Okay, so now we can use example show this how to use the Laplace transform in MATLAB. Ft equals t cubic sine 2t. So for this one, we need to use the symbolic toolbar, symbolic math toolbar. First, we need to define s and t are symbolic variables. So s, y, m, and t. Then type in original function. Then use Laplace transform directly. So now converging is capital Y equals Laplace f t x. So from time domain to s domain. Then after we get capital Y, we can convert back. So just use inverse Laplace. So small y equals I Laplace. So I for inverse. Capital Y S T, so from S domain to T domain. So now we can do this in MATLAB. Okay, so first one, show this. So we use this toolbar, symbolic math toolbar. So S T F equals T caret 3 times sine 2 times T. Okay, so we define this function. We can see works with SYM, they are symbolic functions, or symbolic variables. Then we can use the Laplace transform now. F from time domain to the x domain. So in this one, this is the function. Then convert back, so we can check whether we get the right one or not. So y s t. Okay, so you can see exactly the same function in time. Okay, so this is for this example. Then for homework, so you need to type the following functions for Laplace and the inverse Laplace function in MATLAB. Sin AT, t times sin AT, e power to the AT, t times EAT, so A is a constant. So for this one, so you also need to define A is a symbolic constant in the MATLAB. So for example, okay, so symbolic function. Then A, S, T, then so A is also a symbolic variable now. Then we can define these functions. For example, I use the cosine AT. A times T. Just remember, we have the result. We can get the results from the table. So cosine AT equals, so after Laplace transform, so S over S squared plus H. So we can do this, check in my mind. So Y equals F T S again from time domain to the S domain. So S over S squared plus S is the same as the result in the table. Then convert back. So from the S domain to the time domain. So this is the homework. Just try these 4 functions in MATLAB for the Laplace transform and also inverse the Laplace transform. Okay, so this one, so we already have the function in the S domain. So you need to use inverse the Laplace transform, get the function in the time domain. So when you do this, just take picture and also submit the picture in the MATLAB. Okay. Then for differential equation, the last chapter, we learned how to solve the ordinary differential equation in MATLAB, right? So we use the ODE 45 to get the result. This is the numeric method. Then for this one, we can also use the Laplace transform to get the differential equation result. Okay, the ordinary differential. So now this one, y double prime t plus yt equals 0. So this is the second order derivative. Then for this one, the initial conditions, second order, so 2 initial conditions. Y0 equals alpha, y prime 0 equals 0. This is the first order derivative. Use the Laplace transform on the both sides of this formula. So L, so y prime plus y equals L0. L0 is just 0. L, then this one, so equals L, y double prime plus Ly. So Ly, t is just original y, right? Then this is the second order derivative. After the Laplace transform, so we know equals s squared ys minus sy0 minus y prime 0. Y prime 0 is just 0. Sy0 is s alpha. So this equals s squared ys minus s alpha. Then substitute these two formulas into this function, into this formula. So we can get s squared ys minus s alpha plus ys, factoring ys, so we can get the result in the S domain. So ys equals s alpha minus 3 over s squared plus 1. Again, so define symbolic constant in the MATLAB. Since s a, so we cannot have alpha in MATLAB. So it's a plus c. So y equals s times a over s squared plus 1. Then use the inverse Laplace transform. So we can get the function in the time domain. So I plus 1. So we can get small 1 in the time domain. So actually, this one we can also get from the table. So SA equals, actually we just used this before. So S cosine AT, so equals S over S squared plus A squared. Then for this result, so S squared plus 1, so we know A is just 1, right? So this is cosine T. Then for our the result here, we still have the alpha here. So the result should be R cosine A, alpha times. So let's do this. So SYMS AT, no, so AS. So Y equals S times A over S squared plus 1. Then y, small y equals I plus capital Y s to t. So you can see y equals a cos a times cosine t. So here a this one is 1. So when we use the Laplace transform for the ordinary differential equation, we convert the integration and the derivative to the multiplication and division. So then we make this very simple. Then just use the inverse Laplace transform to the function in time. So this is the result of y equals a. Then for homework, so this is also the second order differential equation. So y prime plus 4yt equals 0. Initial condition are y0 equals 0, y prime 0 equals beta. So first one, just like this. So you need to use the Laplace. So you need to write this process by hand. So use the Laplace transform on these original differential equations. Then get the ys in the s domain. Then use the inverse Laplace transform. Then get the result function in the time. Okay, so this is the Laplace